Recording in progress.
Pero la tiene que compartir la pantalla. Tiene que entrar en el Zoom. Para verla. Vale. Pero yo creo que no va a ser porque pero, ¿cuál? No, porque aquí no se ve también. Tendría que entrar él, ¿no? Gracias, Gianluca. Okay, finally. Oh, sorry for the delay. We were just putting everything in order. Yeah, so I would like to introduce my former PhD supervisor, Michał Holewski. He's working in Gdansk now and for a lot of years, I think. So it's difficult. I mean, I should talk for an hour to say everything he has worked on. So let me just say that now he's interested in open systems and quantum transport. And in the past he did a lot of mathematical things, but now he wants to move towards more experimental stuff. And that is why he came here. So yeah, the floor is yours, Michał. Thanks for coming.
Thank you very much. Yeah, so indeed, I'm now more interested in some real numbers from experiments. So that's why indeed I'm here, and I'm very happy that I can talk to Rosa, to Misha, to Sam, and of course Rika. Okay, we know Rika will be back for a long time already. Good. So I don't want to bother you with some specific topic because I don't know what you are interested in. So I will maybe go through a bunch of things that we do in Gdansk. I do not need to finish this talk. I can stop where we can. Okay, I can answer questions of things. So this will be very loose talk. So okay, so we are in ICTQT in Gdansk. And this is roughly some group of collaborators there. So okay, I will just maybe briefly say about just one slide or two slides per topic, just to say what things we are interested in, or at least all my collaborators there are interested in. There are some bridges sometimes too. So I'd like to do bridges to transport or to mesoscopic physics, to bridge these topics, because there are some possible connections, and sometimes I do not see the connection. This is puzzling, so maybe I would like to think how to make it. So of course, a lot of work we devote to quantum heat engines or just microscopic heat engines, and this is the first example I know of the engine where we have three-level system, and these levels are coupled to the cold bath, and these two to the hot. So the hot makes here a lot of populations, like super hot, like half, and therefore, and because this is coupled to cold, then what happens is that here you get inversion of population, right? It's something like that. Yes, because this again, am I right? I'm repeating it 1,000 times and then I am confused. So maybe you tell me where you should get here you get inversion of population because cold bath tends to make this population large. Yes, it just tends to. Okay, and then here we get this inversion of population, and so that's something like an engine. Because then here you can get work from this. You just shine a laser here and you get photons from this. Okay, so after 20 years, Robert Alicki from our institute has formulated like the theory of heat engines by means of mass equations. So he then defined heat, work, and showed that there is Carnot cycle, that everything works. Okay, and so okay, nowadays we have some quantum heat engines. I like very much this one. Is very fancy setup. So these guys have put. So normally, if you have ion traps, these electrons are like that. And then their trick was to put them like that. So this means that here you have more room in this direction and here less room. And therefore, it is like when you are heated, then you go here. So it's like you then, like it is like an expansion. And if you are cold, then you are more here. So in this way, because of this difference, you can think of really like it's like something like piston and like having more room and less room. So that's very close to some engine that we see in say in a car or something like that. And then there is something completely opposite. I guess transport people know this very well. And here, so there work is just like the energy that we gain. It makes this oscillating more and more. So this is something like, okay, like suppose we have a car and then this piston is just starting to run like crazy, and if we do not take out this energy, then it would just amplitude would grow. So this is like very much like this mechanical engines, and this is something else, yes, because the work is like in form of the current. And I spent a lot of time on, like deepening some foundations of heat work engines, but the notions are more suitable to this picture, where I have some quantum system with some levels. I know, what is later. I would say more. Somehow, all of what I did somehow doesn't fit to this scenario. And I am curious because there are a lot of notions, there are theories developed, but it doesn't apply to this scenario, which is experimentally much better. Like this is much better, much more accessible. You can play with this, and somehow all the achievements do not apply. One has to think how to do it. Okay, so most of the theory of engines or whatever are concerned with some like two-level system. So okay, where the work is collected by some field. So for instance, we have two levels. This can be quantum dot, and then we modulate it with external field, and then we tune the couplings to the environment so that when it is down, then it couples to cold bath, and when it's up, then it couples to the hot. So this is like with the engines in car, they have these valves, which decide in which stroke we are. Good. So this is the engine given. Oh, this is the same paper. No, it's different. Yeah. So in this paper, and so here, so this engine is not autonomous. So you have to have this field which modulates it. You have to do it externally. While we know engines and cars are autonomous, they just run. Yes. So then they propose such an engine where you have, instead of external field, you have simply a resonator, which is coupled with this two-level system. And this is not standard coupling. This is not like James Cummings, where we exchange the quanta. And it's not easy to find this coupling in experimental, like in this setups which you have in experiments, mesoscopic experiments. I recently heard from some guy from Delft that he had such a coupling. So if you spot such a coupling, then I would be very happy to get to know, because it would be great to realize this experimentally. So that would be some resonator talking to a quantum dot, but we need this kind of coupling. I don't know, it's not easy to spot it. So if you have a coupling, then you can, what they did, they just propose some master equation, just derive master equation. And this is similar like that, but here you move levels. And here, these are some virtual, levels. So you have some transition to some, you have now the jazz system used together, the resonator and the qubit. And I like it is like a smallest engine you could think of, which is autonomous and good. So that was dynamical setup, and that can be perhaps implemented experimentally. We spent much time on doing something that is discrete, very mathematical, but we wanted to push the efficiency of the engines to its extreme. So we say we have this our system, and we put it to bath, and we do not only allow some thermalization, but we want to apply here the more the most general transformation that preserve energy. So this big unitary, suppose we have access to everything in the bath, So that's a very fundamentalist approach to try to have the best possible contact. And then we go to this work stroke. So we interact with the bath. That's some black box. We just have some mapping that acts on this. Then we go to the work stroke. So then we are detached from the bath. We just take work from this, and then we again go to the hot bath, or maybe it was opposite direction. And here again, we want to do the most general operation that we can do with the bath. So that was somehow fundamentalist approach to try to have the best possible efficiency. I was unhappy with all this our stuff for one reason, that in experiments, especially in this mesoscopic, as I thought, experiments, is that stuff is strongly coupled always on. And here we say we take it, we attach, we then remove, attach, and so I thought it is not very much related to the real world. But just these days, I am reading a PhD thesis by Ludovico Tesser from the supervisor is Janines Pletz-Tosser. And then he considered this Landauer-Buttiker setup where in the middle we have collision center and this, I don't know, particles of speed from the reservoirs. And it turns out that he presented it. I don't know to what extent it is in the literature, usually it's not put like that, but he presented it really like this. So this is not most general, but it was like, okay, I have I first prepare so one reservoir just speeds particle, then the particle goes to the scattering center, and then it maybe reflected, may go further, but it was very discrete, discrete steps. And from this, he got this average current fluctuations, like in standard approach of in transport. So it's interesting that maybe this discrete approach is relevant for the experiment. Okay, my postdoc André Malavasi likes very much various thermal machines, including not only engines, but also heat transistors. So these are transistors where it's not about electric currents, but heat currents. So by some one heat current, you steer the other. I do not know much of that apart from this idea. So they've done some work. But what I'm doing with them is the following simple thing. Now it's dynamical. So you have one two-level system coupled to the bath, the other coupled to the bath, and they are both coupled to resonator. So this is where work is stored. So this is like an engine. They are not just again, yeah. So this directly they do not interact, but just this resonator is interacted with them in such a way. So this is three-body interaction essentially between these two. And we are, this is bosonic. So, you know, with transport, you have mostly fermions, yes? Okay, bosons are maybe photons or resonators, good. So this we have. Right, so the point is just to, the point is to see what's the exact dynamics, because we solved first master equation, and we saw that, for instance, that this saturates. So this engine stopped working at some point. It's interesting. I thought it will just go forever, but it stopped. So then we wanted to see what's the exact dynamics, and we have some exact, numerically exact. So we are now, okay, we learned how to do that. Ankit knows how to simulate it, and then we will see what's the truth. So that's some work in progress. Okay. Now, yeah. Yeah, to compare, yes, because we think that as far as we understand, master equation should work in that regime, but because it gave some results, we do not know whether to trust, because you know there is some problem, local, global, these things, people, yeah. It just reaches some steady state, which is obvious if this would be connected to the buff. Yeah, because of course, if this connects to the buff, then of course it gets energy, but then it dissipates, and there should be some steady state, yes. But we do not connect it to the buff. So this is funny that simply it stops working even though we do not take energy out of that. Perhaps there is some explanation of that, but we want first to be sure that it's true. So that's why first we want to see the exact dynamics of that. Yeah. If you connect this with that directly, like here. Yes, but after a long time, yes. Because this, I don't know, we couple this in such a way that this gets work. So this is steady, but this is getting work out of that. So essentially this is. Sorry, start, yes. But you know, car goes whenever it has, yeah. Okay. Good. Yeah. So now I would like to say a few things about ergotropy. You know, this is some notion, like people have written like thousands of papers on that, and a lot of. It's very interesting and so on, and it's very like relevant for understanding heat and work. But I don't see how I can apply all this branch of science to a transport scenario. So we have these thermoelectric engines, and it seems that it is not completely not there. Okay, I would love to do some research where I apply this result, this understanding to transport, yes, to thermoelectric engines. But so that's some interesting goal. So let me say a few words. Of course, I didn't do anything about it, just thinking. So let's now just tell what's ergotropy. So if I have, say, two-level system, and it's, let's be diagonal and Hamiltonian, so this is lower energy, upper energy, and suppose this is population, which is larger here than here. So we say then that the steady state is passive. Lowest energy has larger population than one excited level, smallest population. If it's one more, then should be tiniest. Yes, so that's a passive state. While this state is not passive, here it's inverted population. So here you have more than here. So intuitively, we understand that this is something that can give us work. So for instance, lasers based just on these atoms. Yes, we have a lot of these atoms, and then they just go down, and then they give us the coherent light. So now one can ask, okay, how much work I can get from such a thing? And people say, okay, I do whatever unitary I can, and I'm trying to diminish the energy of this, right? So I have some system, I apply unitary, trying to make the energy as low as possible. And then we understand that this energy had to go somewhere, and we say, so that's the work that we obtain. That's very implicit, because I didn't show you where it goes. Yes, I just apply unitary, but you can then make it explicit. You can say, okay, my unitary was done by some laser, and my laser was some coherent state, and this work is in terms of photons that went to this field. So now my field has more photons. So one can indeed justify that this goes somewhere in a nice form. It's not that this energy was dissipated, but it's just in a nice form, because that should be work. Work should be just like taking the energy and like store it somewhere in a nice form. Good. So ergotropy is just this maximal energy that we can take out. So it's just the energy of the guy minus the energy of this passive, because from this we cannot get energy. Whatever you do to this, you only can increase its energy, right? So this is about heat buffs. You have heat buff. Whatever you do to heat buff, you can only increase its energy. And this is second law. The second law is that I cannot decrease energy of a heat buff, because then I would get work, and I cannot get work. Good. So now we thought that, okay, we thought, if I have some system and some bath, and if I think that ergotropy is indeed the amount of work we can draw from a system, somehow we thought it should be impossible to increase the ergotropy by single heat bath. For a long time, I had in mind such a possible second law, yes? You know, this is microscopic, so we have to like refine notion of second law, right? We have to be able to apply a second law to some small system in vicinity of the bath. And that's why, okay, I thought, oh, maybe it's this, that ergotropy you cannot increase because this is some refined notion of how much work I can draw. So that was a candidate, and the ergotropy is some candidate, to be relevant parameter for second law. And somehow in parallel, people knew, and I also realized that you can increase ergotropy by single bath. So an example is that you just take a ground state. So you have two levels, ground state. And it turns out that if you stick it to the bath, and you run James, so even single mode, which is thermal, then by James Cummings, you can make the state make inversion of population. It's slightly not pure, so there is a price. Okay, so there is some interesting question: how much I can increase the ergotropy of this guy? And we have, but you know, where you allow here arbitrary non-cheating unitary, meaning I do not put energy to the stuff. Yes, because of course I can just flip it. I can just go and flip, and then I increase ergotropy. So we should apply now unitary that preserves energy, right? So I do not put energy by hand. The energy should only go from here. And so I apply here some big unitary that doesn't change energy. It commutes with the total Hamiltonian. You can think that I put it to interaction and then I switch off the interaction. It's like collision. It goes. Okay, and then we obtain some bounds. So we said we show that ergotropy of the initial state, final state minus initial is bounded by such a thing. So I hope maybe I'll just explain it later. Yeah, I think I should give some examples later if I have time. Yeah. Yeah, this is passive, yes. This is also supposed passive, like ground state. But if you have two passive states altogether, it's non-passive. Yeah. An example is what? Is hot bath and cold bath, yes? Hot is passive, cold is passive, but if I have them together, I can draw work, so it's not passive, right? What do you mean yeah, good, you're right. So, okay, so what I mean so this is some state, and now in this formula, I consider this state, but made passive. Yeah, so for instance, it was this, so then I reshuffle it so that it is now passive. I just reshuffle the probabilities. So I take my state, and if it is diagonal, then I just reshuffle it. It's not diagonal, then I put it to diagonal, put largest population on the ground state, and then second largest, right? So I compare such state, not this origin, and this is the thing. So suppose this was thermal but inverted. So suppose this is thermal, suppose that was inverted. So then look, this is thermal inverted, but they make a passive version, so I invert back, and then this is 0 because this is thermal. So you see, this is very non-trivial bound, and even often very, very strong. Maybe if I have time, I'll just say more things. So this is some, very. It is some constraints of second law time, of second law type. Yes, this gives you severe constraints for doing something by means of the buff. Okay, just mention that in our institute, people also are playing with some scenario where you charge one system and then with external field, and the system's coupled with the other system. Then you have some dissipation, and then they they consider dissipation to common reservoir, and then they got some results that energy does not go only into one direction and does not go back. This is some interesting interference coming from this collective reservoir. There is very big ongoing question that my collaborators pose, namely whether all engines have moving parts. So, for instance, in thermoelectric engines, you do not see moving parts. You don't see these valves. So in cars we have valves. Yeah? So somehow which tells you, okay, now you are with a hot bath, now we're cold. You have piston. Piston is oscillating, right? So Talitsky and Alejandro Jenkins, they think that they think that behind every engine there is some self-oscillation. So there's the oscillations that appears because of some heat flow. Yeah. So we have some non-equilibrium, and this non-equilibrium creates this self-oscillation. So, and for instance, they're exploring this topic for like almost all kinds of energy transducers. So with this, so one of the engines is actually solar cell, where we have it's an engine exploring the difference of temperature of the sun and of an ambient temperature. So the present theory of solar cells is solely based on some, like it's on Sager-like, meaning based on some steady currents. And they think that this picture is not the essence. The essence should be some self-oscillations. So there must be some mechanism, right? Good, which is okay. Now, also in the topic that these two persons, Robert Talitsky and Alejandro Jenkins, pushed forward was moving baths of various kinds. So what happens if your bath is moving with respect to your system? Yes, what happens? So if it is not moving, then we know that the system in the weak coupling relaxes to the equilibrium state. But what if the bath is moving? Yeah. If it is moving, so then we apply it to a few things. Here it's not moving, but it's expanding. Right? So in cosmology, you know, the universe is expanding. So then they thought, okay, but so let's think that, okay, we have this bath with this temperature of this what is the temperature? This background temperature, and this now expands. So we have expanding bath. Yes. So they have a very general theory of moving or expanding baths, and how it looks like is this, that if your bath is moving, then and in your system you have some characteristic speed, like speed of sound. normally the bath is it's damping, yes. So it's damp you to the steady state. But for moving bath, some modes are not damped but are exploding, and these are those that are related to the velocity larger than the speed of sound. So it's related to shock waves somehow. But it's nice that they use actually some quantum fields approach reduced. So there are some traces of quantum fields, and they even can apply it to the ocean, following to ocean waves, following Zeldovich. Zeldovich was the guy who was hydrophysicist, but then also I think he did first contributions to black hole thermodynamics, right? And they also applied it to explain triboelectricity. So when we move, when we do this, rub one thing with the other, we know that they get the charges passing from. We get things charged, right? So the charge is passing from one piece to the other. It happens with this cat, for instance, if you. So they explain it by just very simple approach. So they say, okay, if I'm moving, so these electrons there see moving bath. So this piece is like moving bath for those electrons, and this piece is moving bath for those. So when they see moving bath, this creates so there are these exploding modes, and these are the modes that transport the electrons. So I like it because it's not that you get something from some calculations, but it's very it's easy to explain it, what happens, right? In words, it's like it gives some intuitions. Okay, we've also done something that is inspired by this paper on Josephson electron pump. So here you have a nanowire, and you run current, and this is superconducting, this stuff. So you run and here you have 3 Josephson junctions. You run current through this. You bias this thing by I think current source. I don't know well, but so you impose current in this direction, and you have here a magnetic field, and this induces current here without bias. So this is not biased, but you get current here. And this is what they call it Josephson pump. Misha does not like the name because they say the following. The idea was the following, that here you have this Josephson phase, which is like a classical, like a classical variable that is like oscillating, and then this works like a pump. Yeah, so that's I think it's good to call it pump because the role the pump plays. Okay, and then we have some different description of Josephson junctions, some phenomenological description that we think is kind of a little for some purpose better than the standard phenomenological description by being RCSJ model, and we consider a situation when this is also superconducting, and we found funny results that I can tell if one is interested. Okay, so how much time do I have? Like, how much time? Like 10 minutes? Oh my God, so long? Yeah, I am prepared, but I care about you because this is not less. It's easier to talk than to hear, yes, than to listen. Yeah, good. Okay. So okay, so my PhD student Gerardo Suarez is extremely skillful in some in simulating dynamics, and he learned these methods, and he's developing with some Japan group the methods which is called HIOM. So that's some exact numerics, which okay, for small system it works. For larger, unfortunately, it needs a lot of resources. So, but by developing these exact numeric methods, he also learned something that can be helpful for also other things. For instance, we have some master equations. Typical master equation looks like that. And if this decay rate depends on time, it's non-Markovian. So it's still like second order approach. It's just, okay, Born Markov, you just cut, all the orders. Not necessarily Markov, but okay, it's a bit of Markov, but definitely it's non-Markovian, meaning it's not, it's really can include some memory effect. And if it is like that, so if this decay rate depends on time, this has lamp shift depending on time, then it's simply not easy to simulate it. It's not like this GKLS, which is called also Lindblad. I prefer these 4 letters because there were 4 people, not one. This is much harder. Why? Just because these guys are some time integrals of the autocorrelation function. And it turns out that this makes most time in calculations. Just these integrals. So Gerardo learned that in this exact numerics, what you do, you represent autocorrelation functions by such a series. So series of exponents. And then what you do, then you analytically do this integral, because this is easy. So once you have this, expression, then you have to sum, because this you compute. And then he came back. So from exact, he said, okay, now let's apply it to non-exact, to just this non-Markovian master equations. And it turns out that he gets a huge speed up by just not computing these integrals, but just plugging in this, doing this analytically, and then, okay. We are also interested in such a thing that if you have not necessarily coupling, just whatever finite coupling between the system and the bath, then we know that the steady state is not thermal. It's not just Gibbs because there is interaction, so it is something else. And people have people have defined this to be fictitious Gibbs state of some fictitious Hamiltonian. And they call this fictitious Hamiltonian mean force Hamiltonian, and the Gibbs state mean force Gibbs, right? So this is the true steady state. And people are devoted a lot of work trying to know what is it. For instance, if you have 2-level system spin boson model, so 2-level system couples the buff, and then people don't know what's the mean force Gibbs state. Yes, so this is not known. Okay, so we have just considered second order approximation, and we have derived analytically second order correction, and here we tested it. So this line, so this is the original frequency of our qubit, and here is the correction. So it's correction in this unit. So you see that somehow, and this blue curve is the correction, and then these are various methods to other like approximate methods. And this dotted one seems to be the best, and this is some reaction coordinate method. Good, so that's this. Okay, I already thought about ergotropy. So now let me see. Maybe I then spend again more time on this in more detail. So it was introduced by these guys, but it's a quantification of this like idea of Push and Voronovich, who just, okay, in a baby version, I just tell you baby version because this I well absorbed, which in baby version is actually something that people knew much before. So that if I have a thermal equilibrium, then by whatever cyclic Hamiltonian, so it starts at some Hamiltonian and you go to the same one, we can only put energy, you cannot get energy, right? So this is, and they define passive state, which is such that you cannot get this energy. It turns out that passive state must be like that. It must be diagonal with the Hamiltonian, it must look like that. and that was the quantification. So not only that you cannot get work from passive, but if it is non-passive, how much you can get. Yeah, so that's the ergotropy. And so let me say a few words on how people wanted to get some second law now with explicit battery, because look here, it was not explicit. This was like some you don't know where it goes and how it goes. So let's imagine that we have now battery. So now our battery is the weight. This is some weight on a rope, yes, and then we getting work means that we shift it up. So you can describe it by some Hamiltonian, which is unbounded from below. That's not very physical. That's some shortage of this approach. So this shift is, the shift is transformation that just shifts me this up and down. And what was the formulation of these people? The formulation of second law was the following. So first to formulate, they said, okay, I am allowed only to use transformations that commute with the shift. Okay, and the work will be defined by average energy change. So I have I apply here some unitary, and then this is somehow a priori that it must commute with a shift. This is how to understand this. If you have battery, you would like that it charges in the same way, irrespective of whether it is, almost full or it is almost discharged. We know that with the true battery, it's not linear, yes, but the nice regime is when it's just they behave the same way all the time, irrespective of what energy it already has. Right? So this is something like that. Okay, and then they're using these ideas, they formulate the second law. So for instance, that the maximal work that you can draw, so you can shift the weight maximally by at most by the free energy change of this guy, where this guy is not necessarily thermal, so this free energy is defined like that. Yeah, so it's not it's just I compute energy of this guy, I compute entropy, and the temperature will be from the bath. So there is this thing, there is a bath, and this is the maximal amount of work I can gain. Okay, we have then worked more, and we say, oh, the maximal amount of work is smaller than the ergotropy change, right? So and then we ask, so how much you can change ergotropy? So this is some version also of second law like. Good. Oh my God, what's this thing? This is funny. I don't know what is this. So suppose I give you a, now let me come back to this. I have some system, yes, nothing else. And now I would like to transfer, now I want to be explicit. First of all, I told you, oh, you apply unitary, you diminish its energy as much as possible, and what you gain is yours. This is the work. So now I want to be more explicit. Where is this work gone? Yes. So then we in this approach, the work goes to the weight. So then this Martin Wobeco, Michael Alberti, he kept this idea of a weight, and then he asked, can I actually really, how I can get this, and what's the price for getting this full energy to my weight? And then he said, well, but look, if I have some state that has coherences, then there are two parts of ergotropy. One is due to diagonal populations, the other is due to coherences. And it turns out that this to get especially this coherent, so this is easily extractable, but for this you have to pay a price. So if you want to draw ergotropy coherent part, also your battery must have coherences. Otherwise you are not able, you will just kill them. So you need coherent battery. But what does that mean, that your battery has coherences? This means that its energy is not well defined. because there is a coherence between energy states. So you have to pay a price that your battery has not well-defined energy. It must have spread. Right? And so before I said, oh, it can be done, but you have to be then careful. What does that mean that it can be done? And here he drawn this picture that, coherent, if you want to draw coherent part, then fluctuations of energy of a weight really grow, right? So there is a price, yes? So and my weight, I will not know precisely where is it. Yeah. So these are these things. So maybe I will not. Okay, so this is the bound that I thought maybe I will skip this. These are some examples. I think I can stop at this point. Yeah, because that was a lot of time. Yeah. Thanks.
Can one calculate the ergotropy for wave function, continuous wave function? I'm trying to think of a way, but it confuses me a lot.
Yes. Well, for instance, so whenever you have Hamiltonian, and whatever state, then yes. So for pure state, that's very easy, because ergotropy is that I have to diminish entropy by unitary transformation. So if I have a pure state like wave function, then what should I do? I should rotate it to be a ground state. So the smallest energy that a pure state can have is just a ground state energy. So this means, suppose let's ground state energy be zero, just for definiteness. Then we see that the ergotropy is just the average energy of a pure state, right? So then it's equivalent to average energy. So it's not equivalent to a mixed state. So this mixedness, this probability makes you that some energy is useless. But if it is just pure, then all energy is useful.
Because the passive state will be
the ground state.
Okay.
Passive pure state is the ground state.
I see. Thank you.
So thank you again.